Okay, we have a little bit of theory left to do with complex functions, and then this is all going to build up towards something really neat, which is solving very difficult problems like fluid flow by just kind of screwing around on Mathematica and thinking of cool functions. So just as a reminder, this is what we covered last time, is that the best way of describing, at least for the theory of complex functions, describing a complex valued function is by having the real part and the imaginary part, right? So complex number goes in, complex number goes out. The complex number has a real part and an imaginary part, x plus z is x plus iy. And we can separate the output of a complex valued function into, likewise, a real and an imaginary part. And you can describe a derivative of a complex function. So, df dz is a thing that you can talk about. It's not obvious that that's true. And you can write df dz, and it exists if it's true for every single possible path to get to your point z0. That's hard to check, so this is really neat. We have the Cauchy-Riemann theorem and the Cauchy-Riemann conditions that these mixed partial derivatives, if these are equal, then the function has a derivative in that region. So it's, again, not obvious that a derivative exists. We would have to check all possible paths as we walk towards some point z. But this does it for us, in the same way that taking a curl will tell us if a vector function is conservative or not. OK, with that out of the way, sometimes derivatives don't exist. We do have non-analyticities. And we describe them with the following terminology. So if there's a point z0 in some region, we say that point z0 is regular if the function is analytic at that point. So if f is analytic, z0 is a regular point. And if f is not analytic at z0, we call it a singular point. So singular, in some sense, I think is really bad terminology. Singular means the derivative does not exist. And that could be for the usual reasons that you're used to thinking of, like it blows up. But it could also be because the thing is not single valued. The derivative is not single valued. So that could be a non-analyticity. OK. So this is the part where complex valued functions give you so much more than you even bargained for or asked for. It turns out that if f of z is analytic in some region, and I'll draw this as we go. So we have some region. Call it R is a bad term, so we'll call it big I. And we've got some point in that region, z0. And then the edge of this region I here be monsters. So these could be a collection of singular points or non-analyticities. And the following two things are true. So if f of z is analytic, and we can check that with the Cauchy-Riemann conditions, so analytic, Cauchy-Riemann is satisfied everywhere inside there, then a lot of really neat stuff happens. One is that it's not just true that the first derivative exists. All orders of derivatives exist. So by checking the Cauchy-Riemann conditions, you not only get the first derivative, df dz, you get all of the rest. So it's what's called smooth. So all derivatives exist. And secondly, the Taylor series about this point z0 exists and converges in a disk that extends out to the first singular point. So let's say that let me just write it, and I'll keep the same terminology. So the usual Taylor theorem, so f of z is equal to the sum as n goes from 0 to infinity of f. The n here would be the nth derivative in brackets, z0, z minus z0. So the polynomial expansion, that's nth derivative, that's nth power. So just Taylor's theorem. So this exists and converges in a disk that goes all the way out until we reach our first monster. So in that case, in my little sketch, it would be here. So this is perfectly well described by Taylor's theorem. We won't use that, but it's good to know, because Taylor's theorem, again, is, it's kind of like the bread and butter of functional calculus. So this is nice. There's going to be something that's even nicer, and we're going to use a very small subset of the infinity derivatives that we do have, and this is a corollary of that, we're just going to use two derivatives. Analyticity certainly gives us two if we have infinity. And with two derivatives, we can do a lot of stuff that we've been talking about, namely solve Laplacians. And that'll be the kind of end exercise of our complex analysis, will be to do conformal mappings and solve some really tough problems just by kind of screwing around and dreaming up weird-looking functions. So our next theorem, but you can see that this is true if you believe that. So we'll again describe a complex valued function, I should say like if. So if f of z, which again we can talk about as u of x and y and v of x and y. So real part, imaginary part. So this is the start of us realizing that there's something really neat going on with expressing functions in terms of complex variables. So this is what I mean by Laplacian. So call it del squared of u and del squared of v. It's 2 d by dx's of u plus 2 by dy's of u. And likewise, Laplacian of v would be 2 d by dx's of v plus 2 d by dy's of v. Right. So each one of these separates the Laplace equation, and this is what this means. Grammar. So, oops, equals 0. So equation means I need an equal sign. So this is the definition of what the Laplacian means, and then equals 0. Okay, so this is true. And that's a different and stronger statement than that. So we say that these are so-called harmonic functions. And as a little corollary of this, I'll just state it. It's pretty clearly true, and I've been doing a lot of writing and not a lot of working. If I have something that's satisfies the Laplacian, then it could totally be the real or imaginary part of such a function. So I'll just say corollary, and not writing the whole thing out. So if I just have some like del squared g equals 0, g could be u or v, right? And it means that if you come up with something g that satisfies this, I could just say like, well, why don't I make it the real part of an analytic function? And I could find v. Right? And so this is what we're going to do. We're going to essentially say, like, we're interested in a lot of physics that satisfies this equation. We're going to just say it's equal to the real or imaginary part of a complex function, find the other part, and then do all sorts of magic stuff with so-called conformal mappings. So we'll do an example of this. So we'll find the so-called harmonic conjugate of some function. So I'm not going to be squirrely about it. I'll just call it u. So we find one of these things, and we'll first show that this is true, and then it's got a conjugate. And the two of them together, when we paste u and v, the v that we find together with this, we will have an analytic function. Okay, so del squared of u is equal to that by definition. We'll just use the other notation. So two derivatives of x, partial derivatives, so we ignore y, treat it like a constant. That's 2, right? So first derivative gives me 2x, second derivative gives me 2, plus d by dy twice on that. First derivative gives me negative 2y, second derivative gives me negative 2. So yeah, that's, for all this heavy terminology, that was pretty easy. So this is very true. So this is a thing that satisfies Laplace's equation, del squared of u equals 0. It's harmonic. This is great. Okay. So now what we want to do is find the other part. So how do we find its harmonic conjugate? This would be maybe a good time to pause, scratch your head a little bit, flip back 2 pages in notes. What is true about analytic functions? So we want its conjugate to make an analytic function. And I have a way of making analytic functions, or checking that functions are analytic, and it has this really nice property that it relates derivatives of u to derivatives of v. So, got it? Maybe, I don't know. So we'll find the harmonic conjugate, we'll say HC, by the CR conditions. So we'll find the harmonic conjugate by the Cauchy-Riemann conditions. Okay. So what that would mean is partial v with respect to y, this is what we're looking for now, is equal to partial u with respect to x. So that's just the first Cauchy-Riemann condition. What is partial u with respect to x? That's 2x, which tells me that v of x and y, good thing we took a little time to talk about undoing partial derivatives, that's equal to 2xy, but, of course, when I took the partial derivative with respect to y, I would have destroyed any function of x only. So there's some unknown function of x that would have been destroyed when we took the partial with respect to y. And we'll just do the same thing with the other Cauchy-Riemann condition and compare them. Okay. The other Cauchy-Riemann condition, dv dx, is equal to minus du dy, partials. And minus du dy is equal to plus 2y. And then that therefore implies dv dx, or v of x and y, is equal to 2xy plus some other function f of y, right? So the partial with respect to x would have destroyed any function of y only. Okay, and then this is v of x and y, this is v of x and y. All I have to do is compare them and realize that if a function is a function of x only and a function of y only, the only thing that I could put here is a constant. So what I have, therefore, is that comparing these, the harmonic conjugate of u of x and y is equal to 2xy plus some constant. Okay, and the only thing to note about this constant is that this constant is a complex number. It could be 3 plus 2i or something like that. So that is our harmonic conjugate. Okay. And what that finally means is that we were given u, we found v, and the punchline of this is that there is an analytic function f of z equals u plus iv equals x squared plus x squared minus y squared plus I 2xy plus some potentially complex constant. So this function, we got this, we generated that part, the imaginary part in this case, from the Cauchy-Riemann conditions. F of z is analytic, and we get all the goodies. So f of z is analytic, you could check it, you would just be undoing the Cauchy-Riemann conditions. And all of those theorems that we wrote down, somewhat boring and laborious they may be, they're really neat. All the derivatives exist. This thing has a convergent, clearly it has a convergent Taylor series because it is a polynomial. And it's smooth, so we get derivatives of all orders. So again, we're going to use this to solve some very difficult problems. And very difficult problems just by kind of like squinting at what the behavior of complex valued functions look like and then how they map the complex plane to different parts of the complex plane.